Howdy, everybody. Hope you're doing well wherever, whenever you are. We're here for day 24 of Advent to Code 2016. We're almost done, and this video I think will be airing near the end of the month or the beginning of November. And I want to do everybody codes, so you may actually start seeing like the previous days and these ones do like 2 per day, just because I want to kind of like finish 2016. And then we'll try everybody codes. And then in December, we'll try Advent to Code 2017. Or sorry, 2025, the year that we're in. So that will kind of be the schedule for the next few months. That being said, I think in November, the everybody codes, they only happen on the weekdays, which is fine because that kind of gives me a break on the weekend. But you know, if there's something special you'd like me to do, or maybe some caddis problems you'd like me to work on in between those, just let me know, and we can start doing those. I thought it'd be fun to do some of the caddises maybe next year. Those are more related to competitive. They're more akin to competitive. I mean, I think Advent to Code and everybody codes are like quasi-competitive in that like people are kind of racing for like how fast can they solve it. But the caddis is more like, here are problems that you might actually get if you were doing like a competitive competition in like a university or something like that. So, which I don't ever plan to do, but it's fun to do that. It might be fun to do that just to learn some of the algorithms and stuff like that. Keep yourself up to speed. So anyway, with that, let's get on to today. It's air duct spelunking. You've finally met your match. The doors that provide access to the roof are locked tight, and all of the controls and related electronics are inaccessible. You simply can't reach them. The robot that cleans the air ducts, however, can. It's not a very fast little robot, but you reconfigured it to be able to interface with some of the exposed wires that have been routed through the HVAC system. If you can direct it to each of those locations, you should be able to bypass the security controls. You extract the duct layout for this area from some blueprints you acquired to create a map with the relevant locations marked on your puzzle. 0 is your current location from which the cleaning robot embarks. The other numbers are in no particular order. The locations the robot needs to visit at least once each. Walls are marked as hashes, and open passages are marked as dots. Numbers behave like open passages. For example, suppose you have a map like the following. Have we done this before? This looks really familiar. Okay. So like here's an example puzzle. I feel like I've done this before. Maybe we haven't. To reach all the points of interest, 2016 day 24. Sorry, sometimes I get weirded out like deja vu. Can you have deja vu but for problem solving? I mean, I have done this day before at some point, because I think I've solved most of the on my main account. I think there's only a couple years that I haven't finished. Anyway, okay, let's continue on. So to reach all the points of interest as quickly as possible, you would have the robot take the following path: 0 to 4, 4 to 1, 1 to 2, 2 to 3, and that would get you there the fastest. Since the robot isn't very fast, you need to find the shortest route. This path is the fewest steps. In the above example, a total of 14. Required to start at 0 and then visit every other location at least once. Given your actual map, and starting from location 0, what is the fewest number of steps required to visit every non-zero number marked on the map at least once? And then here's our puzzle input. It's a little big. Looks like that. So I'm sure it's an eye chart. Sorry. So like 0 starts right here. We are fortunate we have a hash around the entire thing which means we can do some simple things to find neighbors. Like we don't have to worry about going out of bounds. Where are the other? Oh, there's a 3, 6, 7, a 4 in a corner or an inside. Okay. Yeah, so for solving part 1, I mean, again, I feel like we've done this before. Like the way you usually solve these puzzles is like if you're looking at the map, again, this eye chart, it's the distance from any one point to another is like fairly large. And so if you tried to do like a check and you said, oh, is the fastest 0, 1, 2, 3, 4, 5, that would be really slow because you had to like do the BFS from 0 to 1, then 1 to 2, then 2 to 3, 3 to 4, 4 to 5. It's actually faster to cache those checks. Maybe it was a year in like 2024 or 2023. Anyway, the answer is the way that these usually work is cache the you do Dijkstras from like 0 to 1, 0 to 2, 0 to 3, all the permutations. You do like a Dijkstra from all of them. And then based on all of those Dijkstras, you then can do either the held carp or the or just like a straight up permutation of all of them to get to the answer. And I think this is why I feel like I've done this before, because I think we've done the math on it. It's like for n equals 8, held carp is like about twice as fast, but by twice it's like 60,000 versus 30,000. Whereas when you start to get much higher numbers, like say 100, then held carp is superior, way superior. Maybe I can find the algorithm and show you. Okay, here's the held carp algorithm. Oh, it kind of shows you. It's kind of a cool thing because you the way it works is like you're like calculating distances and like kind of building groups. So it is n squared 2n, 2 to the n. But I think it has a high space complexity. Yeah, it's n 2 to the n space. So as the number gets very large, the time complexity becomes better, because remember the time complexity of the normal way is n factorial, and this n factorial starts out small for like the first 8, 9, 10 numbers, but then this quickly remains the shortest because the n squared to the 2n is like substantially smaller than n factorial for large n's. But n factorial technically only requires a space of n, whereas this one requires n times n 2 to the n. And so it's not as, this space requirement can be large for very large solutions. What does held carp say? I mean, I think it gives you an algorithm too. Yeah, here's the algorithm. I kind of am inclined not to do held carp, but maybe we could do it in the recap. It takes, I don't remember exactly how it works. I do remember you're building chains and then you're using, like, the idea is, oh, if I append the next one, which chain should I pick from? And it's probably the chain, the previous chain that was the smallest from distance A to B or 4 to 5. Yeah, you keep like a set of distances. It's this right here thing. Anyway, we can try and solve it with held carp in like the recap or something like that, or I can describe how it works. So I think setting up the algorithm might require more knowledge than I have to just like fumble through and try and remember. So I'd want to like, that's me saying like before I actually do held carp, I'd want to like read it a couple times to make sure I understand what it's doing so I could explain it well enough for you to use it. So I feel like for now we can, because I mean, we can't have more than 10, right? And so, you know, we're never going to do more than 3 million. So, and I don't think it's that, right? I don't know what the largest number is. I can't see it in the eye chart either, but you know, I think we'll just go with that solution. Oops. So like what it will basically be is do Dijkstras to each of the things. And once we've done that, then we can iterate through all the permutations to find the shortest path to travel to all of them. So what do we want our input to be? I think we can leave it as a grid and we can just check for dots. Again, because it's like surrounded by a hash, we don't have to worry about like falling off the map. So we can literally just do like the deltas of like up, down, left, right when calculating. But we will need to know where all the points are. So we'll have a vec point, and then we'll have a vec car shot. Sorry, I've been learning French. So we need type point type struct point, and we'll have x eye size, y eye size, and we'll simple point fn new y eye size will return self x y, and simple add for point type output is another point, and point new self dot x plus right hand side dot x self dot y plus right hand side dot y, and let's derive debug clone copy equal partial equal and hash, because when we're doing the Dijkstras we'll want to have those implemented. Then we have our grid, which I think is just going to be a vec car. So we can do let what are they called? Locations. And then we'll We want to trim dot lines dot map. L. Oh, we want to enumerate these two. L dot cars dot enumerate map. If C does not equal dot and C does not equal hash, we know it's one of our things, so we'll do locations dot push point new xy, and we return a dot. Otherwise we return C. So we're going to collect on that. Oh, it's locations. And then we're going to return. Oh, it's not a vec. We're going to return a vec point and this. I did trim. Oh, I need to dot map. Oh no, this I need to collect. Okay, what don't you like about here? Oh, these are U sizes. Oh, that's crazy. Okay. So now I have my my locations and my thing. So I can say like that. Points. So I'm going to use the pathfinding algorithm to do Dijkstra's. Or to do like a BFS. It is just a BFS because all the distances are one. So I need to have a neighbors function. I think I can actually just do deltas.iter.map. D P plus D dot filter grid dot get p dot unwrap equals dot map p1 collect. I think it's something like that. Or point to point. I can also implement oh, this grid is a vec, so it's not get, it's a grid p dot y p dot x. I got to dereference them, huh? What if I do this? I do want these to be U sizes. They'll never be less than 0. Nope, I can't, because those will be, I can't do the negative ones. So I actually need to do this. This is still a point. And then I need to so the other thing I could do is, oh yeah, here's what I could do is, let's make this, instead of a vec car, let's make it a hash map and fx hash map point car. And then what I can do is this would be flat map, and for this we would return I've done it again up here. I'm very bad at this. Can it infer B? Hmm? Oh, I don't have the surrounding. I actually think now I can do it like this. It can't infer it, but it will be able to, I think, soon. So it'd be like let this equal locations dot iter dot Cartesian product locations dot iter dot map lr if L equals R. Continue. Oh, I can filter map. Otherwise, we want to Dijkstra start is L, successors equal neighbors. Success is like that. We filter map on this for L and R, also for R and L. So let's just flat map. Then this will return an empty. This will return a vec of this and this dot collect x hash map. Trait from inner point. Oh, these points are, so I just do like this. Nope. Does that do it? Looks like I got it in the wrong order. This Dijkstra's returns like the actual path and the distance, I think. This is also R and L. But I need to dereference these. I just do this and this and this and this. Please. Collect cannot for type parameter. Okay. Point. Usize. Why would I need to do default? Am I missing something in the path? Finding Dijkstra. Rust. What does it say? Dijkstra. My n needs to be equal hash clone, which I got. My successor fn, give me an n and I'll give you an in. Item nc. So that's what I'm looking at. And it's saying equal hash clone. I'm supposed to, no, this is right. Some iterator that returns n and c, where c is 0 ord copy. Collect point unsatisfied trait bound. Oh, yes, that's, I don't have the vec down here. Joy. That's why it's mad. You can infer that, right? Okay. So I don't actually have an answer, but you can see it did, presumably did all of the Dijkstras in that amount of time. Presumably then there's 56. Oh yeah, because it's like the eight. Is that right? Okay. I'm trying to think in my head, does that make sense? There's 8 total locations. And so the question is, you go 8 plus 7 plus 6 plus 5. I think that's right. Hmm. Do also need to partial ord. I have to think, why is it that into doesn't work? I need to learn about into. Okay, this is perm. So we want to do each permutation dot map. E dot min. So what is this? It's from the, we're going to do windows of 2. So we'll do p dot windows 2 dot map. Oh, can we also do what is it, tuple windows? So it's something like that. No implementation for pointless. Can't compare point with point. Oh, I did ORD but not partial ORD. Or 12? What are the chances? Man, that took a half an hour to get to this one. But that is the right answer. Okay. So, part 2. Of course, if you leave the cleaning room robot somewhere weird, someone is bound to notice. What is the fewest number of steps required to start at 0? Visit every non-zero number marked on the map at least once and then return to 0. So what's going through my mind is, I mean, this is essentially the same, but we're now only interested in permutations. So dot filter p Whoa. I actually don't know what my locations are. Yeah, I don't actually know what the 0th one is. That's funny. So I need to have this return point where the 0th is. And we say in here, we say if c equals 0, 0 equals point new, x as u size, y as I size. Why do I keep doing that? And then I want to return 0 here. This one I don't care about. Part 2 I do care about it. So we go 0. And then we want to filter where p equals 0. Like that. Plus dists of p dot and -1 and 0. That's almost certainly not right. I think I just had to yeah, it looks like just dereference them once. Why can't this be a U size? $664. That's it. Okay. So what? Again, what did we do here? Like step 1 was calculate the distances from each location to every other location. And that's literally just do Dijkstra on all of them, right? So then go through all the permutations and find the smallest. Use Dijkstra. Could be BFS because we're just everything equals 1. The distances are always like an additional 1. And return or and make a map of, you know, like P1, P2 to dist, right? So now we have some map where we can say like, hey, what's the distance from P1 to P2? And it will give us that. That's what like this is right here. So then we go through all the permutations and that solves them. Do I technically have to do this? I run Dijkstra again, but presumably it solves immediately. Yeah, I mean, I don't technically have to do it because it should be 0, but I'll never have the case where like in my permutations I'm going through it. So that's a little, it is an optimization, but it maybe makes the algorithm less clear. By the way, how do you like to using these turbofish operators, I think is what they're called, or do you like putting them right here? For me, I end up using this, I think, but mostly because if I know what it's going to be and I know it's going to need it, but there's a lot of times where I just don't know what it needs. So, you know, okay. Yeah, and then what does P2 ask you to do? It's like do the same thing, but now you need to start and end at 0, right? I guess I kind of technically did need to do this as well because the robot's starting at 0, right? So that's interesting that I did get a solution. I got the same solution. Apparently this shortest solution, this was doing all of them, but this one I was saying, you know, I technically have to start at 0. I didn't do that on P1. So if I had gotten that wrong, that would have been interesting trying to figure out that bug. On part 2, you definitely want to do it because you start at 0 and then you need to end at 0. And so that's all that changes between this one and this one is I do the same thing, but I just say, okay, after I've calculated my distances between each of my pairs, like going from point 0 to 1 and 1 to 2 and so on and so forth, I also need to add my distance from going to the end back to 0. And so this one becomes the min doing that. And so you can see how fast these run. They run in like milliseconds, right? Again, there's only 8 points. You could probably do held carp and it would speed this up by like, I don't know, 15-20%. Depending on the cost of allocating memory and storing. So I think you store like a bit mask of like the visited nodes and the distances to those visited nodes. The sum of the distance of the visited nodes in the bit mask. So like you're allocating a bunch of memory. But we can do held carp in like the recap, I think. So if I have time. Yeah. I do like the ability to like use functional style things here in Rust. You know, the fact that I can say, oh, do iter, do a Cartesian product, then do a flat map of them. Oh, I didn't need to do this either. Right. Okay. Yeah, sorry, I'm just reading through it, looking to see if there's anything I can improve. The parse kind of looks funky. So this is definitely somewhere we could improve. But like the idea is go through each of the lines, enumerate them. Then for each line, I'm going to go through each of the characters and create my a vec of point cars that are going to be flat mapped into like the FX hash map thing. But I also want to track my locations. And so I update my locations here as well as my zero value. Yeah, I did kind of luck out that I didn't technically have to do this because the shortest path started at 0, or at least one of the shortest paths started at 0. Okay, how did you solve it? Did you do anything different? Maybe you already solved it with held carp. Send me the link. I'd love to see. I think that's the only two ways. Again, I feel like we've for sure done this before. I don't know why. Maybe it's when I was solving some other problem for fun. But there you go. Day 24. We're just about done with the year. So thanks, everybody. We'll talk to you next time. Bye.